Hello everybody and welcome to another math video. In this video I will be going over systems of linear equations in two variables. So what this will include is a quick review of graphing lines. We will then graph two lines on the same plane to solve systems of linear equations. Then I will go over two different methods without graphing, not using graphing, known as the substitution and the elimination, or aka addition method. And then we'll look at some applications at the end. Without further ado, graphing lines. The first thing you want to do is solve for y if you need to, and that includes writing the equation in slope-intercept form. You want to identify the slope and y-intercept next. The third step, you want to begin with the y-intercept, and then the fourth step is you move with the slope and connect your dots and draw the line. We have the only example that I will be working through here. And when you solve for y, if you just follow my direction, solve for y, the only thing that we're going to do is add 4x. And that will reduce, which will leave us with y equals negative 2 times x plus 3 plus 4x. But that is not a graphable version of this line, so we would also have to get this in slope-intercept form, which would be y equals negative 2x minus 6 plus 4x. And we could combine these terms here, the negative 2x and the 4x, to get 2x minus 6 equals y. So if you'll remember, the slope-intercept form is y equals mx plus b. We can find the b, which is the y-intercept here, which is where we will begin, if you will. And m is the slope here, which tells us how to move. So you may notice why I chose the words begin and move up here. All right, let's go ahead and plot that y-intercept over here on the coordinate plane. There it is at negative 6. And then we can go ahead and move using the slope. So again, the slope here is 2. Which means 2 over 1, which means we will rise 2 and run 1 to the right. Rise 2, run 1, rise 2, run 1. And I'm going to keep doing that until I run out of space here. That's good. But I can also move to the left. I just have to do it exactly the opposite way. So left 1, down 2 would keep me in line, no pun intended. Then you can connect all of those points together and get your linear graph. And if you're feeling up for being fancy, you can label this as y minus 4x equals negative 2 times x plus 3. You can actually label that line. Let's move on. Okay. On this slide, there are 3 examples, and of course, we will be graphing 2 linear equations on the same coordinate plane. Now again, in order to be graphing these, you should have them solved for y. That's going to make them the easiest to graph. So to keep this slide brief, I will be solving any equations for y very quickly here. So this system for number 1 will become y equals negative 1/2 x minus 1 and y equals 1/4 x minus 4. So if you solve this second equation for y, that is what you'll get. So from there, we will come down here and graph these linear equations. The first of which has a y-intercept of negative 1 right there. and the slope is -1/2, which means we will go down 1, right 2. So there, there, there. And again, you want to go as far left and as far right as you can, because I have no idea where this other line is going to go. So I want to be able to find the intersection point if they intersect, because that's the point that will work in both equations. All right, the second equation, y equals 1/4 minus 4, will cross the y-axis here at -4, and the positive 1/4 means we will rise 1 and run 4 to the right. Oh, look. There is the point of intersection already, very first or the very second point we draw there. And so I'm just going to freehand these lines. Normally behind the scenes I would bust out a ruler, but I just want to, there we go. So what is the solution to this system of equations? It's that point right there. That point is 4, -3. Now what does that mean? If we take this answer, 4, -3, that means it's a solution for this system, which means if we substitute these numbers in for x and for y, respectively, in both equations, it will make both equations true. And that's really what we're looking for, is we're looking for an ordered pair that will make both equations true. So in this case, it'll be 4, -3. Well, let's just check this real quick here. If I substitute 4 in for x in this first equation, half of 4 is 2, and it's got to be negative. -2 minus 1 is -3, and the y value is -3. So we would get -3 equals -3. Yeah, the first equation is true if we substitute in those values. The second equation, 4 minus 4 times the y value here is -3. -4 times -3 is 12. 4 plus 12? Well, 4 plus 12 is 16. Yep, it works for the second equation. One other thing that you can think of here is that just by looking at this system of equations, I could have told you that these lines were going to cross. And that's because the slopes here are different. So if you have different slopes, then you'll have one solution. Okay, next, example 2. It looks as though I have forgotten a negative sign, so I'm going to put it right here in front of this 2x. Example 2, as we continue here. If you solve for y, you'll get y equals -2/3 x minus 3. And if you solve the second equation for y, you will get -2/3 x, is that plus 4? Okay, so moving down to graphing, the first equation here I will graph in red. So we start at -3 and we rise and run down to right 3. There. Up to left 3, there, and there. The second equation here I will do in blue. So we will start at 4, rise over run, down 3, right 2, down 3, right 2, or down to right 3, my goodness. Down to right 3 there. And up to left 3, up to left 3, up to left 3, something like that. And if you come through and draw these lines, you'll notice that they are parallel. And what that means, as you probably remember, is that they will never ever cross. They will never ever touch. They will never cross. They will never intersect. So one way you can look here is if they have the same slope but different b values, different y-intercepts, there will be no solution. And that's the answer when you have parallel lines with different y-intercepts. Now this last example over here should not take too long. When you solve for y in the top equation, you end up with y equals 5/3 x. What is it? Minus 13/3. Guess what? When you solve the bottom equation for y, you're going to get y equals 5/3 x minus 13/3. So here's the graph of that. In fact, that is the graph of both of those lines. And what we end up calling these are coinciding lines. So just from the system, just by looking at it, you can see they have the same slope and the same y-intercept. So if you have the same slope and y-intercept, then you will have infinitely many solutions. And that will be the answer here. Now there is a way to parameterize this answer, and that's just a fancy way of saying that there's a very mathy way to write down what, like this ordered pair here, what would be the ordered pair that works here. There's a way to do that, but I do not teach that at this level of math. We just want to get the basics down. So on to the next topic. What happens when you try to graph three equations in the same plane? Well, in this, I try to introduce here the idea of single variable linear equations. So just as maybe it's a review for most of you, if not all of you, x equals 4 represents a vertical line. And how I like to think of it is whatever variables are in the equation represent the only axis that they're allowed to touch. So if there's an x in the equation, we have to find this number on the x-axis because it's only allowed to touch the x-axis. And because it's not allowed to touch the y-axis, it would have to be parallel to the y-axis, which means this line right here would be x equals 4. For the next one, y equals -2. That is a horizontal line. We have to find the -2 value on the y-axis, which is right here. And this line is only allowed to touch the y-axis, so it'll be horizontal to the x-axis. There we go. That is y equals -2. And then this last one, we have y equals 3x minus 8. Now, I may not have been saying this last time, but it didn't pop into my head until right now. There is both an x and a y in this equation, which means the graph will cross both the x and the y-axis. So it has to have some slant. It's not going to be vertical. It's not going to be horizontal. So we'll start down here at -8. We will move up 3 to the right 1, and we will keep doing that until we get, I guess that's it. And I will connect all of those points together. Woo! Let's try that again. Close enough. Pretend it's perfect. All right, from here, we're just trying to see, is there a single point that all three lines pass through? Well, it seems as though if we look at the black and green lines over here, they intersect at 4, 4. So we know one solution that works for a couple lines here, or at least a point of intersection, would be 4, 4. Another point of intersection, we could look at, let's see, the black and red line. Just look over here for a second. I'd be willing to bet where the black and the red line cross would be at 4 for the x value and -2 for the y value. Let's take a look. Oh yeah, look at that. 4 for the x, -2 for the y. That's right where those two lines cross. All right, so we have a 4 and -2 here. That's another solution. And then the last one is where the red and green lines will cross. And the red and green lines cross at 2, -2. But none of these points lie on all three lines. So the answer for this system has no solution. But that doesn't mean that the lines don't cross. And soon enough, where those lines cross is going to be playing a very big role. Let's move on to a brief overview of substitution and elimination. Solving a system algebraically, meaning with no graph, can be boiled down into two different ways. We have substitution, that's one way, and elimination, that's another way. I'm going to start with substitution. It's generally good for two different situations of systems of equations. The first of which is there's a variable with a coefficient 1, or it could also be -1. That's usually also pretty easy to figure out here. So 1 or -1. Or if you can see that there are a pair of identical, I'm going to say variable terms in both equations, then you can also use substitution. From there, once you notice that, you have to solve for one of the variables. Either you have to solve for the variable with coefficient 1 or -1, or you have to solve for one of the terms, but not all the way. You'll see in an example very shortly. You isolate a variable and then substitute an expression into the other equation. As far as elimination is concerned, this generally works in almost any situation. And this, in fact, is my favorite method. I do not like the substitution method because it's not as versatile. But with the elimination or the addition, or you may say elimination by addition, it requires you to multiply either one or both equations by a scalar that's just a constant, as long as it's not 0. And then add the equations to eliminate a variable. And with this, we're looking for opposite coefficients. That's what our ultimate goal is. If we have an equation, two different equations, and the y's have opposite coefficients, then we're set. If not, then we're going to have to make them opposite coefficients. So once you do both of those things, either for substitution or elimination, you solve for the variable, then back substitute to solve for the other variable. I think it's just best to look at some examples. So let's go ahead and look at some substitution examples. On this slide, substitution examples. Go figure, I just said. So what we are looking for in the equations, first and foremost, you want to just see, is there a variable here, a variable term, with a coefficient of 1 or -1. And yeah, it's right here. This is the term with coefficient 1 or -1. And to make things a little bit simpler, I'm just going to call the top equation equation 1 and the bottom equation equation 2. And I'm going to do the same thing over here for this real quick while I'm remembering about it. So here we go. We have a variable term with coefficient -1. Let's solve for that x. So for equation 2, I'm going to negative x. I'm going to subtract 8y from both sides so I can start isolating the x. So it'd be negative 8y plus 1. Then you can divide everything by -1 because that's that's the coefficient multiplied to x. So we can get x equals 8y minus 1. So what do you do with that? This is all equation 2 that we've been working with. We know what x equals. We can then substitute this, whatever this is, in for x in the other equation. We have to be using both equations here. So this will end up being 3 times 8y minus 1 minus 4y equals 7. From here, we can just solve for y pretty simply. That's 24y, that's -3. So let's see, this is 24y minus 3 minus 4y equals 7. So what do we do from here? I guess we can combine these y's together. That'll be 20y minus 3 equals 7. We can add 3 to both sides to get rid of that minus 3. And then we can divide by 20. So y equals 10 divided by 20 is 1/2. Ooh, fractions. All right, well, sometimes you have to deal with it. And that's why it's good that we're using substitution. You would never be able to guess 1/2 on a coordinate plane by graphing. Oh, there's some extra usefulness to this, is that it helps with fractional answers. Anyway, so y equals 1/2. That's half of our answer. We don't know what x is. So how do we figure out what x is? Well, we can just take this 1/2 and substitute it into this equation. So 8 times 1/2 is 4. 4 minus 1 is 3. X is 3. All right. So we know that x is 3 and y is 1/2. So we write that as an ordered pair, 3, 1/2. That's it. There is substitution example number 1. Substitution example number 2, again, we're looking for identical variable terms in this case. If you look at the variable terms, I've got a 3x and a minus 3x and a 5y and a 5y. None of those have a coefficient of 1. But since I see a 5y here, what I can do is I can substitute this negative 3x plus 16 in place of the 5y, because that's exactly what 5y is equal to. I have 5y equal to all of this, so all of this can be substituted in for 5y. That's pretty nice. We don't have to deal with any fractions this time. So let's get blue. There we go. So I will have 3x plus, it's not 5y anymore, it's negative 3x plus 16 equals 4. So negative x plus a negative 3x plus a negative 3x cancels out. We're just left with 16 equals 4. Ooh, that is not true. And since that isn't true, this is... So if it's not true, our answer is no solution. Okay, let's take a look at elimination. 2 elimination examples here. And something I didn't mention when I was going over the elimination concept over there a few slides ago is elimination works best when you have all of the variable terms on the left side of the equation and all of the constant terms on the right side of the equation. So when I take a look at this first example here, I have all the variables are on the left side of this equation, but I have to be able to distribute this 3 so I have separate terms to work with. But this 2 minus 2y, that needs to get moved to the right side, the left side of the equation. So I'm going to arrange these in such a way that I will have distributed this and I will have moved this term to the left side of the equation. So the new system with equation 1 and equation 2 will be something that looks like this. It'll be 3x plus 6y equals 13, and negative 3x plus 2y equals 3. Now, the big deal with elimination is that you want to not only have all of the variables on the left sides of the equations, but you want the same variables first, like the x's. You want the x's first and the y's second. Generally, alphabetical order works the best. So that being said, the next thing we need to look for is opposite coefficients. And opposite coefficients just means same number, opposite signs in front of the same variable. So x's are 3x's here, there are negative 3x's here. That's what we're looking for. So that being the case of what we're looking for, we can add these equations together. The 3x and the negative 3x will reduce away, and that leaves us with 6y plus 2y, which gives us an 8y, and 3 plus 13 is 16. Now this is a pretty easy solve. We can just say y equals 2. Lastly, again, this is only half of the answer. We have to go back and figure out what x is. Now, it's a little bit different here. We could use either equation, and we could have used either original equation in the substitution method as well. But the one where we had solved for x already was going to make it the easiest. Unfortunately, we don't have that this time around for our elimination method. So what I will do instead is I will choose the second equation here, and I will substitute 2 into the second equation for y. So negative 2 times 2 is negative 4. Negative 4 plus 3 is negative 1. So what that tells us then is negative 3x equals negative 1. Which means x equals 1/3. Yeah, x is 1/3. That's more fractions. All right, just hope you all get used to those. So this is 1/3 comma 2, x comma y. That's our final answer here. Okay, next example. I do not like what's going on here. I have an equation 1 and I have an equation 2. Everything's already nice and lined up for us. You can see we have all the x's first, all the y's second. Fine and dandy. I've got equation 1 here. I've got equation 2 here. That's fine too. But this 3, I don't like this 3, not even a little bit. I think the first thing I want to do is get rid of that 3, which means I'm going to multiply the entire equation here by 3. Just one equation. And I'm doing that simply to get rid of a fraction, and yes, you're allowed to do that. So if I multiply that entire second equation by 3, I'll have 2x minus 3y equals negative 6. That's fine. And this will be negative 8x plus 12y equals 24. Okay. So with this is going to require elimination. We don't have we don't have two identical terms here, two identical variable terms. No, we don't have a variable with a coefficient of 1 or negative 1. Nope. So we'll have to make opposite coefficients. And you can choose out there. You can pause it and try it. Do you want to eliminate the x's or the y's? But this one's actually going to require some multiplying, and it's only going to require multiplying to one equation, I think. Let's eliminate x's. All right, so I see here I have 2 x's and I have negative 8 x's. How can I make those numbers opposites of each other by using multiplication? Well, the most efficient way to do that would be to multiply the first equation here by 4. In a mathematically inefficient way to do this would be to multiply the top equation by the coefficient in the bottom equation. So we could take this negative 8 and multiply it up here to the top, and we could take this positive 2 and multiply it here to the bottom. And what you'll notice is that that will give us a 2 times a negative 8, which is negative 16, and a negative 8 times 2, which is a negative 16. So we're really close. We're really, really close. We need to change the signs of one of these numbers that we're using over here so that the signs here will be opposite when we multiply. And because I like positive numbers, and I hope you do too, I'm going to change the negative to a positive. So let's run that distribution again. 8 times 2 is 16, and 2 times negative 8 is negative 16. So this will give us the opposite coefficients we need. All right, so the top equation times 8, or equation 1 times 8, would be 16x minus 24y, ooh, that's a lot, equals a negative 48. The second equation would be negative 16x, and you can see we have the opposite coefficients there, plus 24y equals 48. A lot of these numbers are the same. I'm concentrating on the x's right now because that's what we were trying to eliminate. So all of the x's are gone. Fine. All of the y's are gone. That's 0. Negative 48 plus 48 is gone. What's going on here? 0 equals 0. Ah, okay. That's true. So this means there are infinitely many solutions here. So anytime you are left with only numbers like this, after you eliminate, if they're the same number, if you get the same number on both sides, it's true, and you get infinitely many solutions. If you get different numbers on each side, then it's false, and you get no solution. Just like back on the last slide with the substitution, we got 2 different numbers on either side of an equal sign that made it false. Back in substitution, if you get the same number on both sides, that's true. That's how you would get infinitely many solutions with that. Let's take a look at one application and then we can be done. All right, we have time for one application problem, and this one is going to deal with supply and demand. So here we have a supply price equation. Here we have a demand price equation. And P is the price, and Q represents the number of pounds of apples. And then we have this following question. If P, the price, is $6, what can you say about the supply and demand of apples? And that's not too bad. What you do is you'll substitute P into both equations, and you'll figure out what the quantity is, the number of pounds of apples. Let's see here. So if the price is $6, I'm just going to do the top equation so you get a feel for how this works. 0.08Q plus 5.15. So if the price is $6, we can solve for Q, which means we can subtract 5.15 from both sides to get 0.85 equals 0.08 Q. And from there we can divide by 0.08 to get 10.625 pounds. And you can do something very similar to the demand equation. And when you substitute 6 in for P into the demand price equation and solve for Q, you'll get 58.09 pounds. So what's happening here is that the demand for apples is outweighing the supply of apples. People want apples. That means when you go back to your farmer's market or whatever with your number of apples, you can charge a higher price for these apples because people want them. And very similarly, if the demand quantity is less than the supply quantity, the price will go down. If you show up with your to the farmer's market with more apples than people want, you will probably discount them at the end of the day just to make sure you can sell what you have. So we have this, the price increases, the price decreases. Where's that sweet spot? The sweet spot where you know if you show up with a certain amount of apples and charge a certain price for apples, they will all sell. Well, that's what we call a break-even point. So the break-even here would just be to solve the system. And since these equations are already set up for substitution, right, we have a variable term with coefficient 1. In fact, it's already solved for P. So we can just say this expression can be substituted in for this P, and we can go through and solve for Q. So here we would have 0.08 Q equals, plus 5.15 equals negative 0.21 Q plus 18.2. And so the break-even quantity that we would need here would be 45 pounds of apples. And the price for all of this should come out to be $8.75. So you'll be selling 45 pounds of apples for $8.75 each, which amounts to about 20 cents per pound, if you want to think of it like that. All right. I hope this video helps you get a better understanding for systems of equations. Good luck, everybody.